Good afternoon. So I'm Dan Freed, Director of CMSA. My pleasure to welcome you to the annual Bott lectures. This is the first of two lectures. Tomorrow's lecture will also be here at 4 o'clock in the afternoon. Before I forget, the most important announcement is that there's a reception after this on the 4th floor of the math department in the lounge. Everyone's invited. So Raoul Bott was, of course, a beloved professor here at Harvard, a great geometer whose work spanned all parts of geometry, topology, analysis of differential equations, and Lie groups, and also a big interest in physics, particularly the second half of his career. So it's very fitting that our speaker today is Andy Neitzke from Yale, whose work also mixes all of those things. And today he's going to tell us about Abelianization in analysis of ODEs.
Right, so thank you very much. So it's a great pleasure and an honor for me to be able to give these lectures. Thanks for coming. I want to tell you about a kind of program that I've been, in some ways, working on now for quite a long time. And the basic philosophy is that, somewhat unexpectedly to me, various problems in math and physics which involve, so we'll study a problem where the data that we start with is a manifold. I'll call it M. And a group, and I'll take the group, so a Lie group, and I'll take the group to be always, just for the purpose of this talk, I'll take the Lie group G to be GLNC. So some problem involving a manifold and n by n matrices in some way, that they can be reduced fully reduced to something much simpler. Problems involving, well, now I have to, okay, so how do I do? So I understood that for the purpose of the Zoom, I have to write pretty big. So is this big enough? That's good, okay. If it gets smaller, please remember. So we start out with some manifold, and in the examples, it'll be a 2-manifold or a 3-manifold, but this seems to be a more general thing. The group GLN, that they can be reduced to problems involving a manifold M twiddle, which is a branched n-fold cover of M. And on M twiddle, we're going to study a thing which is somehow much simpler. It's going to be simpler because it's going to involve not GLN, but GL1. So we're replacing the non-abelian group, which is complicated by roughly in some sense, we're going to reduce to diagonal matrices, but the more precise thing to say is that we're going to take a branched n-fold cover, and we're going to study GL1 problems on this branched n-fold cover. And that reduction won't be complete, and we'll need to introduce one additional thing, and the additional thing will be defects of various codimensions. So the picture we're going for, because this is somehow the main picture that you want to have through the talk, let me just emphasize the picture. So the idea is we have M, we're doing some GLN thing here, and we're going to replace it by M twiddle a branched n-fold cover. Here, I guess n equals 4. And we're going to do a GL1 thing here. And we're going to have to introduce, so in the bulk, this reduction will be complete. But then there will be some defects, some extra places where we have to insert something. And that something will be accounting for the part that we miss in going from GLN to GL1. So OK, that's very vague in general. So let me say what the examples will be. So here's the kind of problem where this picture is supposed to apply. So the first one, and I think the only one I'll talk about today, is something very classical. It's the analysis of ordinary differential equations over Riemann surfaces. Order n. So the idea is you try to study some differential equation of order n, and you reduce it to performing, roughly speaking, you reduce it to performing ordinary integrals, which is like studying a differential equation of order 1. But the integrals that you do, instead of being on the surface where the equation was defined, the integrals live on some covering. And related to this, closely related to this, there's the geometry of moduli spaces of Higgs bundles. And then, so that'll be the main example for today. And then in tomorrow's talk, I'll talk about some other problems. One is the study of classical Chern-Simons theory, classical Chern-Simons invariance of connections over 3 manifolds. Then another one is the theory of skein algebras, or let's say quantum invariance of knots. Knots or links. So here the picture is going to be that you have a 3-manifold and you have some link in the 3-manifold, and computing the quantum invariance, like, the simplest example would be if the 3-manifold is S3, then you might be talking about like the Jones polynomial, and that'll get related to some computation on involving a covering of your 3-manifold. And then the last one, in some sense the most interesting one, is conformal field theory, 2-dimensional conformal field theory. So the construction of conformal blocks. Which also, somewhat to my surprise, seems to fit into this picture. So this is some very general machine. Its origin, so my interest in this started with some work I did here with Davide Gaiotto and Greg Moore. And here it was motivated by a problem in supersymmetric quantum field theory. These other ones are sort of less clearly connected to supersymmetric quantum field theory. So I would say we have all these stories. The exact way in which they're connected is not, to me, 100% clear. So there's some bigger story here which is kind of waiting to be discovered. OK, so let me start telling you about the first one. And OK, so what do I mean by Abelianization? Let's start with something very simple. Let's start with one matrix. OK, so here's a fact, which I think you know. Suppose I'm given a matrix, call it A, and let's say A at SL2C. So a 2x2 matrix with determinant 1. Given a matrix which is generic, if I look at that matrix up to conjugation, there's a normal form for such matrices. normal form, which is that it's conjugate to a matrix of this form. Right, a generic matrix in SL2C, you can diagonalize, call its eigenvalues A and A inverse. And you can put it in this normal form in a finite number of ways, exactly 2 ways, right, because you can exchange A and A inverse. So in 2 different ways. And so you might regard this as like a simple example of Abelianization. Here we have something in SL2C, we reduce it to something in GL1. Okay. Now how about if you have 2 matrices? Let's see. Okay, maybe I come over here. How about if you have 2 matrices? Okay, so suppose I'm given now 2 matrices, call them A and B in SL2C. And again, and suppose that they're generic. So I'll describe something which you can do for most pairs A, B, a dense open subset of all pairs A, B. Okay, so now let's consider them up to simultaneous conjugation. So if I can conjugate them separately, of course I can diagonalize both of them. If I consider them only up to simultaneous conjugation, then typically if I take generic matrices, they will not commute, right? So you don't expect to have a normal form where you just diagonalize both of the matrices. So it's actually an interesting question. At least to me, it's not completely obvious what's a reasonable kind of normal form to look for 2 matrices, 2 non-commuting matrices. So here's one answer. It's not, so here this was somehow a very canonical answer. Here I'll give you an answer which is slightly less canonical, but still, as it'll turn out, it'll be very useful. So, and I'm going to write it first and then explain it. So here's what it looks like. I can conjugate A and B simultaneously into a form, and I'm going to write it. In principle, I could write it as a single matrix. I could do the little product I'm about to write, but let me not do that. It'll be more useful for me to write it as a product of matrices. Okay, so there's the form of A, and here's the matrix B. I can put it in this form. 0, 1 over B, B 0, 1, 1, 0, 1. Okay, 0, 1, minus 1, 0. Okay. So the claim is that if you have any generic pair of matrices, it's always possible to conjugate them into this shape. So here, my normal form here depended on one number. And you could think, if you like, yeah, here I didn't say it, but I should have said, this number A, you can think of as like a local coordinate on the moduli space describing the situation. The moduli space, just the space of matrices A up to conjugation. So that space is one-dimensional. There's a local coordinate, which is just this eigenvalue A. Here, we have 2 matrices up to conjugation. And now we have a parameter space which is 3-dimensional. And it's coordinatized by these numbers. So here, in my matrices, I have 3 numbers appearing. I have A, M, and B. Local coordinates on the moduli space. Pairs of matrices, again, up to simultaneous conjugation. So, and just as before, this normal form is not quite unique. It's almost unique. You can get it in 2 different ways. So, So if someone gives you a pair of matrices, I'm saying if someone gives you two generic matrices, you have a normal form for that pair of matrices up to a discrete choice. So if you like, there's the coordinate a, b, m, and then there's another coordinate a prime, b prime, m prime. But either one of them, if you choose one of them, that gives you a local coordinate system in a neighborhood of your given pair of matrices. Okay, now, so as I go on, I'm going to try to convince you that this normal form is actually useful. But let's first say where it comes from. So, how would you prove this theorem about pair of matrices? So here's the idea. It's the most convenient way that I know to prove this. Is to draw a picture. So let's draw the corresponding picture. It makes this obvious. So how do we prove this fact? So let's think of it in the following way. Let's think of this A and B not as just two disembodied matrices, but let's consider the manifold. Let's consider a two-dimensional manifold, a torus with a puncture, once punctured torus. So here's a picture of a once punctured torus. So I'm putting the puncture at the corner. So these edges are identified and these edges are identified. So that's a torus with one puncture. And now you could think of A and B. So the fundamental group is just free on two generators A and B. And so think of A and B as being, if I start at, for example, this, choose a base point, say this point. And then we have the parallel transport along this arc. Call that A. Well, sorry. So I could think of my pair of matrices. Think of A and B. Give a representation of pi 1 of m into SL2C. So A represents this loop and B represents this loop. And so then we could think of this. We could think of that representation geometrically. We could think that what we have actually is the data of a flat SL2C connection over the torus. Given a flat SL2C connection, its parallel transport gives me this representation of the fundamental group. So equivalently, we could say I have a flat SL2C connection. Nabla over m. And now, so now I want to take these parallel transports and I want to factorize them in this funny way. So that corresponds to the following kind of picture on the torus. Let me draw. Let's draw a picture. So maybe I'll draw it here a little bigger. So okay. Now I see I've made one strategic error. Sorry. Let's make these yellow. Yeah, good. Okay. So I take my torus and I just draw on it this kind of stratification, where I've marked two different kinds of codimension 1 things. I've got these dashed lines, which I'm going to call branch cuts, and I've got these yellow lines, which I'll call walls. So let's. And so now I can reinterpret this factorization as saying that I can put my SL2C connection in a very particular kind of gauge. I can put it in a gauge where the parallel transports along, in each domain, the parallel transport is always going to be represented by a diagonal matrix. The only time when you see anything that's not diagonal is going to be when you cross either one of these yellow lines or one of these dashed orange lines. So we're kind of, so the matrices didn't commute, so it'd be hopeless to diagonalize everywhere, but we're doing kind of the next best thing. We're diagonalizing on all these open domains and putting some very specific defects that contain the non-diagonal part. So let me write what I said. So my claim there that we can factorize the parallel transport is equivalent to the claim that we can find a gauge for this connection such that the transport in each domain is diagonal. The transport across one of the cuts is that's going to be these matrices. That's going to be these permutation diagonal matrices, so strictly off diagonal. So strictly off diagonal. And the transport across these yellow ones, those are somehow the really interesting ones. The transport across the yellow ones is upper triangular unipotent. So you see it here with ones on the diagonal. So then, yeah. So this specific form here, this specific form of the parallel transport comes from finding a gauge for your connection that has these properties. So then it's an interesting exercise. Why is it that you can find such a gauge? So the idea, how do you find such a gauge? So so what you do is in each domain, so we have these domains that look like this. So each of the domains of the picture topologically looks like this. And so to find a gauge means we have to find I have to find some particular basis of the two-dimensional space where my flat connection lives. And what I'll do is I'll use the eigenvectors of the monodromy around the puncture. Anyway, so it's indeed possible, if someone gives you a generic SL2C connection, it's indeed possible to put it in this kind of sort of stratified picture. Okay, now, how do I think about that, that stratification? So one useful way to think about it is the following. Suppose that I would erase the yellow walls. Suppose I would modify this connection by just erasing now all the unipotent matrices. So suppose we erase these walls. Then what's left? So then what do we have left? So then all the remaining parallel transports are given just by diagonal matrices, except when I cross one of these cuts. When I cross the cut, I have a strictly off diagonal matrix. So one way I could think of that is that I have a GL1 connection which is living on a double cover of my manifold, and the double cover is branched exactly at these dashed lines. So what's left is the parallel transport of a GL1C connection. I'll call it nabla twiddle, defined over a double cover, branch double cover, M twiddle over M. So it's a double cover which is branched exactly at these 2 points, and the way I'm presenting it by giving explicit branch cuts at these dashed lines. So branched. So it's branched at these points. So from that point of view, finding this special gauge, another way I could think of it so our fact about the existence of this kind of special gauge for the connection says that, so it says that, so we have this connection nabla twiddle, GL1 connection over M twiddle, and we're identifying our connection downstairs, our connection over the base. We're identifying it so our connection over the base, we're identifying it as the push forward of this GL1 connection on the cover away from the walls. So the picture is we started with the SL2 connection on the base, and now we're replacing it by this GL1 connection over the cover, and then the local coordinates that we found, so the coordinates on the moduli space, which were A, B, and M. So the coordinates A, B, and M of the connection nabla, we can interpret them now as the holonomy of this abelian connection nabla twiddle along loops in the double cover M twiddle. I can draw those loops. Well, in fact, they're just the lift of these. They're just the lift of these loops here. So for example, A. So now it's a parameter just living in GL1. It's the holonomy of the GL1 connection over the lift of that loop to the double cover. Here's the holonomy B. And then the holonomy M is just a little loop that goes around the puncture. There's M. OK. OK. I hope that wasn't actually too explicit. So just to repeat the basic statement is that given a kind of generic representation of the fundamental group, in other words, a generic SL2C connection over M, we've replaced it by nabla twiddle, a GL1C connection over a double cover M twiddle. And then and that map is a local isomorphism of moduli spaces, meaning if I have a connection here, this map is kind of locally bijective. In particular, if I take the holonomies of this connection here, those are just some simple numbers that I can build out of the connection. Those give me local coordinates on the moduli space of connections here. OK. So this construction, so I was laying it out for you in the specific case of the one punctured torus, and I wrote some explicit equations, but it's a more general thing. So let me quickly say, what's the more general picture? And then I have to show you how this thing kind of occurs in nature. So more generally, suppose C, suppose M is any compact surface with punctures. So I take a compact surface and then I puncture it at finite many points. Then given an ideal triangulation of M, we can draw a stratification similar to the one I drew in the case of the once punctured torus. So the picture is we've got our surface M. It's got some punctures. Then I fix an ideal triangulation. And then I draw the same kind of picture that I drew before. Namely, so I'm going to make, again, a kind of ramified double cover. I'm going to make a ramified double cover of this surface, which is branched at one point in each triangle. Then I'm going to draw these walls. And then again, I'm going to have a similar situation where I start out studying the representations of the fundamental group of this surface. OK, that's some complicated thing. They parameterize the SL2C character variety. But I get a kind of simple coordinate system, a simple way of thinking about those representations by mapping them to GL1 representations, flat GL1 connections over a double cover. So we again get SL2C connections. So flat SL2C connections over M, called them nabla. We map them to flat GL1C connections over the double cover M twiddle. And again, it's a local isomorphism of moduli spaces, meaning that if I just look at the holonomies here, I get a local coordinate system on the moduli space here. OK. OK, so I think, so now I spent a long time telling you about this construction, and it might seem like something that it might not be clear why anyone would want this construction. It gives you coordinates on these moduli spaces, but so what? But now what I want to say is that these coordinates actually show up very naturally when you start considering problems, natural geometric problems. Okay, so here's an example. So we're going to study now not just arbitrary representations of the fundamental group, but representations of the fundamental group that have a kind of geometric origin. We're going to study things that come from actually solving a differential equation. So now, suppose, so up till now, I was taking M to be kind of just a topological surface with some punctures, but now suppose that it's actually a Riemann surface. So suppose M is a Riemann surface. So we're going to study a kind of complexified version of the Schrödinger equation where the coordinate lives on this Riemann surface. So the full data that I have to fix, I have to fix a spin structure and a complex projective structure. A spin structure is some discrete choice, which you can almost forget about. A CP1 structure means you pick an atlas of charts where the coordinate transformations are Mobius transformations. You could think of the simplest case where the surface actually is CP1. That's fine. Then it automatically has a CP1 structure. And then the last thing is let's fix a meromorphic quadratic differential in the surface. So what's a meromorphic quadratic differential? It's something which, when you write it in local coordinates, it's written P2 of z dz squared as the transformation law for P2 of z dz squared. But locally, you can just think it's a function. So it's a section of the canonical bundle squared. P2 is a meromorphic function. So given that data, we can write down a kind of complexified version of the Schrödinger equation. So this data determines Schrödinger operator. It's a differential operator. D h bar comma phi 2. So it acts between, it's a map between two line bundles over the surface. But what will be mostly important is just what it looks like in local coordinates. So in local coordinates, so in local coordinates, d h bar phi 2, you would write it as h bar squared d by dz squared plus P2 of z. And now we solved the equation. We're interested in solving the equation. So we consider the equation dh bar comma phi 2 psi equals 0. Whereas in local coordinates, it says h bar squared d by dz squared plus P2 of z acting on psi of z equals 0. Okay, so that's a second order linear differential equation. It's exactly the form of the, like, if instead of z I'd written x here and I was on the real line, then this would be exactly the usual form of the Schrödinger equation. The parameter h bar, so I take h bar to be just any complex number. And what we're discussing here is kind of a global version of that makes sense on a compact Riemann surface. Okay, so now, given this equation, we want to understand its solutions as well as we can. Now, the solutions typically won't be some, in all but the most trivial examples, the solutions won't be some explicit functions that you can write down. So to know the solutions concretely means, for example, to know some invariants, like to know their monodromy around loops on the surface. So a concrete question we could ask is, suppose I have a solution of this equation, and I take it around a loop, how is it transformed by monodromy? In other words, so analytic continuation of the solutions of this equation, let's write the equation star, gives a representation rho h bar comma phi 2 of pi 1 of the surface to SL2C, or equivalently a flat SL2C connection over the surface. And we can ask, what is that representation? So the question, what is it? So given some particular potential, what's the corresponding representation of the fundamental group? So even more concretely, if you're given some particular loop on the surface, you could ask, what is the trace of rho h bar phi 2 on that loop? To know the representation, it's sufficient to know the trace of the holonomy around every loop. Okay. So that's a concrete question, but it looks hard because to solve it, we have to somehow integrate this differential equation. We have to concretely say something about the solutions of this differential equation. Okay, so now here's the claim. So the claim is, here we've got some representation, and I claim that the good way to study this representation is to use exactly the coordinates that I was talking about before. Let me try to formulate that precisely. Okay, so here's the theorem. Well, yeah. So let's let. So I wrote rho h bar phi 2 for the representation. I'll write nabla h bar phi 2 be the corresponding SL2C connection. Over the surface. And now the theorem is that, so there's a kind of technical assumption, which is that phi 2 has to have at least one pole of order at least 2. So very recently, I think it should be possible to remove this assumption. But so far, oddly enough, this is a situation where having poles actually makes the problem easier. And so let's suppose that your potential has some poles somewhere. So then, the statement is, so first of all, nabla h bar phi 2 can be Abelianized in the sense I described before, to a connection, GL1C connection, over a double cover, branch double cover, GL1 connection, nabla twiddle, over the branch double cover C twiddle to C, defined by C twiddle, is just I have my potential phi 2, and that determines for me a double cover, which is just the two square roots of the potential. So it's given by the equation y squared plus phi 2 of z equals 0, sitting inside of the cotangent bundle to the surface. So when I have a Schrodinger equation, I have this canonical double cover, and the claim is that the Schrodinger equation kind of naturally gets reduced to a GL1 connection over the double cover, where I have to tell you where the walls are. So let's see. I have to continue the theorem over here. So then the holonomies of Nabla-Twiddle, the holonomies of this Abelianized connection, so I call it Nabla-Twiddle. Let's call it Nabla-Twiddle H bar phi 2. Holonomy of Nabla-Twiddle H bar phi 2 around a loop gamma on this double cover. So let's call the holonomy X gamma of this connection, it's a Abelianized connection on the double cover. It has, so we said these are like coordinates on the moduli space of connections. So if I could give you a formula for those quantities, it would be the same as completely knowing this monodromy representation. So you can do almost that well. So what we can give is you can give a complete asymptotic expansion around h bar equals 0, where the first term, so I'll just write x gamma of h bar is the exponential of, so the leading behavior is like 1 over h bar times some number, and we'll say what that number is. And then there's an asymptotic series in powers of h bar, where the z gamma is the integral around the loop gamma of, okay, I guess the slickest way to say it is lambda, where lambda is the Liouville 1 form on the cotangent bundle of C, or the way that you kind of concretely study it is, what is that 1 form concretely? It's the square root of P2 dz. So concretely, suppose you have some loop, and you want to know the monodromy of your Schrodinger equation around that loop. The statement is, right, sorry. I have to say one more thing before I can say that. So these are these abelian coordinates. And then what you're actually interested in probably is the traces. So any particular trace, any trace of holonomy that you might be interested in. So trace, the trace of the holonomy of rho h bar phi 2 around a loop P has an expansion that expresses it as a sum over loops on the cover with some integer invariance, some integers And then, so there's some integers which appear here. And then there's these functions, x gamma of h bar. So what does it mean? As a practical matter, what does it mean? It means, suppose I have some loop on my base surface. Yeah, we'll draw the picture here. So suppose I've got my base surface here, and I draw a loop on it, and I want to know what's the trace of holonomy around this loop. So what this theorem says is, okay, well the exact formula is somehow complicated, but let's just talk about like the leading term in the expansion around h bar equals 0, like the first thing you would see in the limit of small Planck constant. So what we say is that the trace of the holonomy that it'll go exponentially like some period where this period is the period of some loop on this double cover. So here we have C, then we have the double cover C twiddle, and this loop here is going to get mapped to some loop on the double cover. So okay, double cover, not that fast. Right, double cover is some more complicated surface, and somehow we have to map this loop to a loop on the double cover, so part of the theorem then I mean, the theorem gives you a little more than just this statement. It actually gives you kind of a concrete way of computing these integers and finding out, given the loop here, what's the corresponding loop going to be on the double cover that computes that determines the asymptotics of the holonomy. So Z gamma, let's write again what I wrote over there. Okay. So okay, so that's an example of this phenomenon where a problem on the base gets more naturally solved by replacing it with a problem on this double cover. So in the last couple of minutes, let me just say a little bit about why this theorem is true, how this theorem gets proved. So, I mean, somehow the main content, yeah, what's the main content of what I've been saying? What I've been saying is that, if someone gives you a flat connection that comes from a Schrodinger equation, then it's possible to put it in this very peculiar kind of gauge that I was describing in the first part of the talk. So why is it possible to do that? That's the thing I need to tell you. So the idea of the proof is we look at the equation. So here's the equation that we're interested in. And to say that you can put it in this kind of diagonal gauge is like saying that somehow you want to produce, putting it in diagonal gauge is like saying that there's a canonical basis of solutions up to a scalar multiple. So you want to produce two distinguished solutions. Of this equation up to scalar multiple labeled by the two sheets of the covering. So we had this, we have a surface C, we have the double cover, C twiddle, whose two sheets correspond to the two square roots of P2. And so in order to put my connection in this kind of special gauge that I showed you at the beginning, what I need to do is I need to somehow produce for you two solutions of this equation. Is I have to show that there exist two solutions of this equation labeled by these two sheets. So how would you do it? OK, well, this is something that's very familiar to, at least heuristically, it's very familiar to physicists who study the Schrödinger equation. So the idea, well, you look at this equation, and you say, how do I solve this equation? So the first try at solving this equation would be to just write, OK, well, let's write psi of z is the exponential of h bar inverse times integral of square root of minus p2 of z dz. OK, now we have to look at this for a second and see why is this a reasonable thing to try. So imagine that you thought this is your solution. So you take two derivatives of this, and what do you get? Well, the first derivative pulls down a factor of h bar inverse times square root of minus p2, right? The second time you take the derivative, you pull down another factor of the same thing. So that looks exactly like it solves this equation, right? You get one square root of p2, another square root of p2. So after you take two derivatives, you get exactly p2, and so it exactly solves the equation. Now this is not right. OK, if it was right, then the whole theory of this Schrödinger equation would be somehow trivial. It's not right. The reason why it's not right is that the second time you differentiate, you have to differentiate the term that you pulled down the first time. But up to that, it's right. And in particular, that error term is subleading in powers of h bar. So what that suggests is that for very small h bar, this will actually be correct. And so it suggests that you can build a solution. You can build an actual solution by correcting this by just adding terms with the lower powers of h bar. And so that's what you do. Sorry, with higher powers of h bar. So let's integrate now a form, all right, lambda of z, where lambda of z is a sum of one forms defined on this double cover, n equals 0 to infinity, lambda n, h bar to the n. The leading one is the square root of minus p. So notice it's not well defined on the base. I need to choose a square root, but it is well defined on the cover. So I take the integral to go from some base point z0, doesn't matter what it is. I take it to go up to a point y of the cover, which is a preimage of my point z downstairs. And so that way, if this works, I'm going to get two solutions labeled by the choices of y, which are the two sheets of the cover. That's exactly what I want. I want two solutions up to a scalar ambiguity, which is this choice of z0. Two solutions labeled by the two sheets of this cover. Now, what is the hiccup? The hiccup is, and this is what causes all the kind of subtleties in the theory of WKB. The hiccup is that this sum, so you can calculate, you can determine all the higher lambda n's in terms of lambda naught systematically just by requiring that it solves the equation. So all these higher lambda n's are completely determined. And the problem that you discover is that this sum actually never converges. This is not a convergent sum. So this gives a formal solution only. Not an actual one. And now, OK, and I'll just take 1 minute and then I'll be done. Just to say what's the key thing that gets you out of, that makes this method work. The key thing is that although this series is not a convergent series, nevertheless, it's possible to make sense of it through Borel summation. So there's a procedure, the procedure called Borel summation for finding a function that's asymptotic to a given asymptotic series. It doesn't always work, but for this particular series, it's now been proved. So it can be Borel resummed. So this was a kind of folklore for a long time, but now it's a theorem due to various people, including Kawai, Takei, Kuike, Shafki, and most recently, I think the definitive thing is being done by Nikita Nikolaev. So the statement is that you actually can make an actual solution by this procedure, but it doesn't work everywhere on the surface. It works almost everywhere on the surface. So this Borel summation produces the actual solutions that we're after, but not everywhere, only off of some codimension 1 locus, some walls. And that codimension 1 locus is exactly the kind of thing that appeared in the first part of the talk. So I was drawing this kind of picture, and I was saying we're going to study a connection where we Abelianize it on the complement of this picture. And the point is that these walls are exactly the places where this Borel summation procedure of resumming the asymptotic series fails. And so for that reason, it produces the kind of picture that I drew in the first part. OK, well, there's certainly more that I should have said, but I'm out of time, so I think I better stop.